Hello, everyone. Thank you so much for your time. My name is Sean, and I'm from Stanford. And this is a joint work with folks at Barefoot Networks, Chang, Robert, JK, Milad Shin, and also Nick McEwen. So today I'm going to talk about a pretty provocative topic about simplifying the data center switch by pushing the network to the edge. And I'll tell you what that is about throughout this talk. So first of all, let's think about how a switch is built today. And I'm talking about the hardware switch, but you could also think in terms of a software switch like OVS. So given a switch, regardless of its uses, it's usually defined in two pieces inside a switch. There's a data plane piece, and there's also a control plane piece. And as we all know, the data plane is responsible for doing packet processing, storing forwarding tables, and doing match action on it, and also some extra data plane registers that you could use for different purposes. And for control plane, and the data plane runs on a hardware ASIC. And for control plane, it is responsible for implementing the routing protocols and having some runtime API driver that talks to the data plane. And usually, this all sits in a software called Switch OS, which is a modified version of Linux or a different daemon that runs in Linux. And this all runs on a CPU. So this got us thinking, how will a data center switch look like in 10 years? As you can see, this original switch design came from internet and enterprise network, and it evolved from that. But as you all know, data center is a different beast. So we were starting to thinking, how will this design change, or if it will, how it will change. But first, let's take a step back and see how the data center switch design evolved from. So let's think about the characteristics of an internet and an enterprise network. First of all, it has an unknown and/or unpredictable network topology. Because the internet is mostly unknown, the protocols need to be very complex to actually learn the topology and adapt to different changes that happen in the topology. Secondly, internet has a bunch of different devices, so it needs to support legacy protocols. That means that more logic and resources must be dedicated to the switch to support all of these different protocols that exist from the beginning of time. And also, there are no trust and control over the end host. You could have any clients join the internet, so definitely you don't have any trust over them or control over them. So any network state that you want to manage has to sit on the switches and be confined within a switch. Lastly, the data plane cannot be changed. Most data plane today runs on a fixed function switch or a fixed set of protocols that we have. Therefore, you cannot use custom logic, and custom logic has to be handled outside of the network or the data plane. So people began to think, we need a switch OS, we need a control plane to actually support all of these things that I've just mentioned. And that's how switch OS came about. Now, let's try to see what switch OS actually does. So here we see a diagram of a bare metal switch sitting on the bottom. And it has two pieces, the CPU board, which contains the CPU and the DRAM and fan, LED, and other sensors, just like a regular commodity server. And also, it has the packet processing board with the network interfaces, like QSFP ports, and the switch ASIC that actually does the packet processing. And top of it sits the switch OS, or people call it control plane. And it is responsible for first implementing the routing protocol daemons, BGP, OSPF, and etc. And if it doesn't run those protocols, it has an OpenFlow agent in terms of an SDN world, where the OpenFlow agent talks to, say, a centralized controller to receive the forwarding tables or routing table entries. And this requires some sort of a L2, L3, or OpenFlow APIs and a data plane abstraction provided by the hardware vendors to talk to the switch ASICs. And this lets you write the forwarding tables down to the hardware. And miscellaneously, you need a user interface, CLI or GUI or some sort of API to read the forwarding table entries. You need some status daemons to read the status of the switch. And you need other miscellaneous functions such as bootloader to bootload your, install your Linux operating system. You need some miscellaneous hardware management, and this is all part of the Linux kernel. So this is how a Switch OS looks like, and as you can see, it is very complex with various different functions, and it's highly customizable. And let's see how complex it is. So here's a list of Switch OSs that are commonly used throughout the industry. Open Network Linux is one of the open source ones, and as you can see, there are thousands of files with 100,000 lines of code. And there's various other versions of it. There's Sonic, which is maintained by Microsoft, which also is very complex and large. There's Facebook's open switching system with similar order of magnitude of complexity, and other Switch OSs from other industry that are unknown, somewhat proprietary. So we don't know how it looks like, but I'm pretty sure they're also as complex as the other open source versions, if not more. And it has been published that 50% of network failures happen in the control plane. And as you can see why, because maintaining this huge set of software is not an easy task. And these companies have many people working on these Switch OSs. And in order to support a Switch OS, as you've seen in the previous diagram, we also need a CPU board, which consists of, say a server-grade CPU, gigabytes of RAM, and gigabytes of hardware. And the parts cost for them, just for the part itself, and also the power consumption is not negligible. And think about in the data center scale with tens of thousands of switches, it could get very, very expensive. So let's put on a simplest hat and think about how to design the simplest data center switch. And this is what we strive to do in this talk. In order to do that, let's first think about how a data center network is different from an internet or an enterprise network. So a data center network has some sort of a central authority, which could either bring up the VMs or machines or a switch, and in the SDN world, put the network topology, logical network topology upon the switches. And there are hardware or software switches with a predefined topology sitting in the network, and that they talk to the end host based on the policy or based on the policy given by the central authority. So looking at this, the characteristic of the data center authority, again, there exists a central authority, unlike the internet or an enterprise network, which means that complex logic could be offloaded. For example, a lot of the network policies are already offloaded to the central authority. And the network topology is known and generated, which means that we could use much simpler routing protocols. We don't have to go back to L3 protocols, which attempts to learn the entire network topology. And also, a data center uses only a small unified set of features, which means that less resources required on a switch. It is known that Amazon runs L3 on their data centers, and Facebook just runs BGP on their data center. So the switches don't need to support all the legacy protocols or different set of protocols that exist today. And we also have more control over the end host, and which means there's more trust over the end host. So we could move the state management off to the end host and manage less states within the network. And finally, data planes could now be customized with the advent of programmable chips, or OVS is already programmable by itself as a software. So we could actually implement protocol that directly communicates with the data plane instead of offloading the communication layer to the control plane. So going back to the diagram, let's do an exercise of which of these pieces we could eliminate. First of all, given that we could use a simplified protocol, we could get rid of the protocol daemons. And given that we could talk directly to the data plane, we could get rid of the OpenFlow agent and also have some sort of an in-band telemetry mechanism to get the data plane states directly with using control packets. And now we don't need an OpenFlow API, L2, or data plane abstractions. And we also don't really need a user interface because we no longer have a forwarding table. And since we don't have to install any of these bootloaders, and we also have, the switches already come with a system on a chip type, something called OpenDMC to install, say, the Linux or do miscellaneous hardware management. We don't really need them to lie on a Switch OS. So we don't need a Linux kernel on it. And that means that we don't need a CPU and a RAM on the switch board. So you can see how this exercise makes us think that we don't really need a Switch OS. And if we do that, if we follow the same pattern, there's also some changes that happen on the data plane side. Usually the data plane looks something like this. We have the match action graph or logical data plane view, as you can see. And you have a switch pipeline that translates the logical pipeline down to the actual logic board of the switch. And since we don't have all of these protocols to support, we could basically have a much more simpler data plane as well, given that the switch OS is eliminated. So when thinking about how to design the simplest data center switch, we come to a question: why do we need a switch OS? And Riley is a network design using extremely simple switches with no switch OS. We're not saying this is the best design or the most efficient design. We're saying this is the simplest design with using the extremely simple switches. So going back to the diagram of a data center design, we already have a central authority. We modified it to also be a part of central control plane, similar to the SDN world, but it will do a little bit more job than an SDN central controller. Switches will now be very simple with no switch OS. And endos come with a kernel module added, a network kernel module, we called it Riley kernel. But this is a customized kernel that stores the current topology of the network and updates it accordingly to the signals that it receives through the data plane. And also the forwarding in this model is a very simple source routing scheme, unlike doing IP forwarding or etc. That's why you need a Riley kernel on the endos to append the path that the packet takes throughout the network. So using this model, we have run some experiment using hardware Tofino switches. And IP performance over two switches over 40 gigabit length were very comparable. As you can see, there are about, say, 5% maybe overhead using Riley protocols. And this performance overhead is mainly from our customized kernel code. And we are looking to improve the kernel code and bridge this gap much smaller. And also, we ran some real-world jobs to see that Riley protocol is capable of running complex operations. And these jobs range from small file transfer to complex Spark jobs. As you can see, the completion times for file transfers or Spark jobs are very comparable for short-running jobs, say a small file transfer, to long-running jobs. Say a page rank over large graph. So although IP performance may be a little bit lower, on the real world job completion times, they are most likely to be equivalent. And since we added the kernel, the custom kernel to our endos, we wanted to see how much more resource the endos uses. And as you can see, the endos usage are very comparable. The endos in Riley consumes a little bit less user space CPU, but consumes a bit more kernel space CPU because since we added a custom logic to the kernel. And it consumes a bit more memory usage to store the network topology, about 3 megabytes. And as you can see, this memory usage varies between the data center topology, but for this experiment, we used the topology of size around 4,000 switches. And we also see that there's a significantly less resource usage. First of all, looking at the CPU and RAM, Riley uses 0 of them. We basically shut off the CPU part of the switch and made it not use it, basically. Whereas in IP world, the switch daemon that runs the protocol consumes around 7% CPU on average and consumes around 400 megabytes of RAM with 25,000 forwarding entries. And that's about the maximum that a hardware switch might support. And the TCAM, SRAM, and match action unit numbers are normalized. But as you can see, running IP protocols consume 2 to nearly 170 times more resources overall. So Riley, again, is a data center network designed with very simple switches, with comparable performance, comparable real-world performance, with significantly less resource usage. So we are looking to take this forward and in the future do some scalability experiments on large-scale data centers or large-scale simulations to make this more feasible. And yes, that's all for my talk, and I'm happy to take any questions.
We do have time for questions. The mic working?
Since the control plane is pushed out, how is the data plane being programmed? Can you get rid of the PCI access as well?
Sorry, can you?
Can you potentially get rid of the PCI access as well into the data plane ASIC?
Well, I guess it depends on the implementation. Currently, the PCI board is still required to program the data plane for the, because the switch that we use is a programmable Tofino switch from Barefoot. So we need to compile the P4 program, which has the data plane logic.
I see. To program the P4 you need, but actually to populate the forwarding tables, you really don't need it.
In this case, we're running source routing, so we don't have any forwarding tables. So that's why we don't need a PC. Yeah.
Oh, I see.
Yeah.
You are pushing the so now here you have to trust the end host, right? You are letting the end host decide where to go. Now the switch cannot enforce any policies or anything. If the end host decides to misdirect packets to other tenants, it can do that.
Right. The end host could be malicious, but first of all, there's a central authority that could will publish the topology. And it could publish the topology based on some policies. Say you want this endos to only go through a certain set of switches or talk to only a certain set of endos. So it doesn't need to give the switch all of the topology. It only needs to give a subtopology to the network to ensure the policy.
I don't know if this mic is working. Oh, great. So I always like this because it sort of plays into my thesis of networking considered harmful. And also to the obvious evolution of, or the obvious sort of realization that data centers are supercomputers and that the network is simply their interconnect. And if you look at, Google, Facebook, Amazon, Microsoft, they all really just want an RDMA fabric. They just want to get rid of the network entirely so that you don't waste all this time doing the sorts of things that you would need to send a packet to, Australia if you're just sending it within the same rack or somewhere else in the data center. My question for you is that, we've seen this a lot, right? Sourcey, for example, just a few years ago, proposed the same thing. And so I guess the question is, what has changed now to make this sort of more feasible or effective? And also, I'm interested in how it's relevant to Open vSwitch. If networking is considered harmful, maybe we don't need OVS either.
Right. So source routing has been here for decades, as you mentioned.
But Sourcey is a good example from SIGCOMM from just a few years ago, proposing pretty much this exactly, right? Right.
But what Sourcey lacks is the ability to retrieve status from the switches. So OpenFlow is somewhat of an attempt to simplify the switch by moving the control plane somewhat to a centralized entity, right? But it still requires an agent to run on the switch. Now, since we have a programmable data plane, you could also program, say, an OpenFlow protocol in the data plane, then you don't really actually need a control plane anymore. So that's what we're attempting to do, taking SDN a little bit further and taking OpenFlow a little bit further, simplifying the switch even more.
We have time for one more question. Please go ahead.
Hi. So when you start showing what you do, it's look exactly like InfiniBand. Did you consider to use that? Because it's also
Sorry?
you can use the switches without CPU. It's a well-known protocol that's lived for more than 20 years, already deployed in
What is it? What is the protocol?
InfiniBand.
InfiniBand, I see. Actually, it's even to support InfiniBand, I guess we have to think if the data centers actually run InfiniBand in most places. In this case, we could append, say, custom protocols on top of our protocol and still run traditional workloads.
Yes, but you still need to use new switches, simple ones.
Yeah.
You change all the equipment that so you're not reusing anything.
But InfiniBand, can it also retrieve status from the switch and send it
Yes.
out to the? I see. I'll have to look into it as well.
It's well used, and you can try it.
Okay.
All right, let's thank our speaker. So our